Here's one more regression example. We'll begin again with a correlation test. A study was done to determine if a linear correlation exists between tail lengths in inches of wolves and their weights in pounds. We'll use a 0.05 significance level and the sample data below to test the claim. Okay, and that should be a decimal right there. There we go. So we'll start by looking at the scatter plot. Now I have already entered the data. This time I put my X values in list 3. So you can see 10, 13, 19, 19, 20, 20, and so on. And my Y values in list 4. So 10 is paired with 79, and 13 with 72, and 19 with 100, and so on. Okay, so now we'll create our scatter plot. So second, stat plot, enter twice. That turns it on. Select the first type of plot, and my X values are now in list 3, so let me change that from list 1. I'll say second and list 3, and then my Y values are in list 4. Second and 4 will give me list 4. I'm going to keep that same mark. Okay, so now we want to zoom, and we want 9, which is the zoom stat. Okay, so there appears to be a bit of an increasing Y value as X's are increasing, so it's worthy of us to continue with this test. Okay, so we have an alpha of 0.05, our sample size is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 sets of ordered pairs. Okay, so we'll find our null hypothesis, which is always rho is 0. No linear correlation between the two variables. H1 will always be rho is not 0. So we have a two-tailed test. Make that a colon. Okay, and we have a critical value to find. Test statistic we'll get from the calculator, a p-value from the calculator, and we'll make our decision. So let's look at our decision diagram. There's 0, perfect positive, perfect negative. Now to find our critical values, we have an alpha of 0.05. It's a two-tailed test, and n equals 10. So it's a two-tailed test, alpha 0.05, n equals 10. So we have plus or minus 0.632. Okay, and let's put them down here. Here's minus 0.632, and here's plus 0.632. And let's shade. I'll just shade with this color. These are our critical regions. Okay, now we're ready to run our test. Stat, tests, linear regression t-test. Okay, remember my X values are in L3, list 3, and my Y values are in list 4. Frequency's 1, two-tailed test. We don't put anything in this field, and calculate. Okay, so my p-value is 0.06668. To 4 decimal places would be 0.0667. My R test statistic is 0.6. Okay, so 0.0667 is my p-value and 0.6. So 0.6 is going to be here. It's not in the critical region. My 0.0667 p-value is not less than alpha, so I fail to reject the null hypothesis. Let's write our conclusion. There is insufficient evidence to support the claim that a linear correlation exists between tail lengths of wolves and their weights. There is insufficient evidence. Remember, the evidence comes from the sample. To support the claim that a linear correlation exists between tail lengths of wolves and their weight. Okay, so that concludes the test for a linear correlation. The next part of the problem asks us what proportion of the variation in the weight of wolves is explained by the linear relationship between tail length and weight. So recall, we get that from the calculator, and that is r squared. And it's literally the square of r. So you can see 0.6, and we have 0.36 for r squared. Which means 36% of the variation in weight is explained by this linear relationship between tail length and weight. So we've found that there really isn't a strong linear relationship, and we're not surprised to see this small percentage of the variation being caused by that linear relationship, or explained by that linear relationship. Well, let's write the regression equation. Even though we haven't found a relationship, our calculator gives us this result. Remember, what we're looking for here is A and B. Those are the parts. Remember, the A is the y-intercept and B is the slope. So A is 40, B is 3. Here's our format, and now let's fill it in. Okay, that's the regression equation. And finally, let's predict. Find the best predicted weight of a wolf with a tail length of 18 inches. Well, now, we have concluded that there isn't a linear correlation between tail length and weight. So even though we can write a regression equation, it's not appropriate for us to use it to predict the weight of a wolf with a tail length of 18 inches. When we've concluded that there is no linear correlation, the best predicted value for the weight of the wolf is the average weight of the wolf. So in this case, the best predicted weight is y bar. Remember, y is weight, so it's the average of the weights. It doesn't matter what x is. X could be 10 inches, 20 inches, 30 inches. We won't even use that because we said that there is little correspondence between these two, that it doesn't have a linear correlation, so the best prediction is to use the average weight. So we go back to our calculator. Recall that in our stat edit, our weights were in list 4. These were the weights of the wolves. So what I need to do is run the descriptive stats, edit calculate one variable statistics, in list 4, my weights. I don't have a frequency list, so just list 4, calculate. Now don't let this be confusing. It says X bar, but X is just what data did you just give the calculator? I gave it my column of data of weights. For my purposes it's Y, but this X bar tells me the average of the values that I put in. There were 10 weights and the average is 100. So don't be confused by that. It's Y bar for our problem, it's X bar in the calculator. That's the average weight of a wolf, and that's our best estimate, that point estimate. Okay, so what we've seen from our two examples is that sometimes we find a linear correlation between the two variables, and when we do, we use the regression equation for the prediction. When we do not find a linear correlation between the two variables, we just use the average of the y values.